Hi everybody. What I want to do in this short video is to, number one, recap what we had been talking about in class last time, Bose-Einstein statistics, and in particular we were looking at photons. So we want to talk about that, and then I also want to do another example for you, similar to the one we did in class last time. So just to remind you, the Indian physicist Bose had written a manuscript where he had treated photons as if they were gas particles, and he deduced how to count them, how to treat them statistically. And he could not get this manuscript published, and so in 1924 he sent this manuscript to Albert Einstein over here. And Einstein, of course, recognized the importance of this work, rewrote it in, I think, German, and then had it published. I think Bose had initially sent it to Einstein in English. So Einstein, of course, did what Einstein does, and it was something important like that, and he built upon that, and that's what we'll talk about next time. Okay. So here we are. We have our photon gas representation up here. We got a chamber and we got a bunch of photons going around in it. What we have to remember is the number of photons in this chamber is not constant. Photons can be absorbed by the walls. Photons can be re-emitted. So the number of photons inside the cavity is not constant. Now, we know that the distribution of photons as a function of energy will look like this. Well, we'll have a product of two functions, Bose-Einstein. So this would represent the number of photons with energy between E and E plus dE, a little more. This is the Bose-Einstein distribution. This dictates the overall shape of the distribution. And then this thing here, what we call the degeneracy, is again a weight. It tells you how important each energy is. Some energies are more important than the other. So this can be a function if you have a continuous set of energies. Or even if you don't have a continuous set of energies, we can approximate this as a continuous function. So this is the degeneracy, and we found out that this, let's go ahead and write it like this. This is equal to, we have an 8 pi. We have the volume of the cavity, so big V is the volume of the container of the photons. We have hc cubed here. We have E squared dE. And then we have the Bose-Einstein function here, which 1 over this, where we have the normalization constant, the E alpha there. Then we have E raised to the E, this is energy, this is kT, Boltzmann's constant times time. Then we have -1 for the Bose-Einstein distribution. We talked about this before, that this is the normalization constant, but to match experiment we find, and because again the number of photons doesn't remain constant here, Einstein tells us we should set alpha to 0, so E to the alpha is equal to 1. So now if I want to find the number of photons, and in fact, since I don't always know the volume, maybe I want to know the number of photons per volume. So I'm going to write this like this: number of photons per unit volume equals 8 pi. I've divided by a volume, so I don't have that V in there anymore. C cubed. Now I'm going to integrate over all possible energies. So from 0 energy to infinite energy. Then I have E squared dE, and then I have E over kT minus 1. So that is going to be the integral that I need to do. So let's go ahead and do that. We've done this before already. What I'm going to do is do a little substitution. I am going to replace E over KT, K being Boltzmann's constant, T being the absolute temperature. I'm going to replace that with X. So I'm going to do a little substitution here. When I do that, then this distribution becomes 8 pi. I had an E squared, but now I'm going to have an X squared. But E is X times KBT. So I'm also going to get a KBT, or a K, Boltzmann's constant, T. I'm going to have it squared here because I have the E squared. And then I'm going to have another, instead of dE, I have a dx, so I'm going to get another KT. So I'll have that KT cubed. I still have HC cubed down here. And then I have e to the now x instead of e over KT minus 1. So to get the number per volume, I need to do this integral. Zero to infinity still are my limits. X squared dx, e to the x minus 1. Now, if you can look in almost any integration table for definite integrals, this is one that you'll see where I'll write it like this: x to the n minus 1 over e to the x minus 1 dx is equal to this, where you have the gamma function, and then you have a series, an infinite series, 1 over 1 to the n power plus 1 over to the 2n power plus so on. Okay. Now the other thing that we'll need to do this is, if you have the gamma function, I'm going to use something else other than n here. Gamma to m plus 1, that's the same as m factorial. Okay, so we go back up. Let's just look at this integral right there. Move this up a little bit. So my n minus 1 is 2. So that means my n is going to be equal to 3. So I'm going to have that integral, 0 to infinity, x squared dx, e to the x minus 1, all that's under the integral sign, is equal to gamma of 3. And then I'm going to have 1 over 1 to the third power plus 1 over 2 to the third power plus 1 over 3 to the third power plus so on. Okay, so gamma to the n equals 3 is going to be 2 factorial, which is just 2. So this is going to be equal to, my integral is going to be equal to 2 times 1. 1 over 1 to the third is 1, plus 1 over 2 cubed is 8, plus 1 over 3 cubed, that's 1 over 27, and then we could go on. But I'm going to stop there. And I'm going to say this is approximately equal to this. So if you add up 1 plus 1/8 plus 1/27, you get 1.16. So you get 2 times 1.16, and that, we'll just leave it like that for now. Okay, so that's the integral. So what I have at this point is the number per unit volume of photons that I have in this chamber are equal to 8 pi Boltzmann's constant times the absolute temperature cubed over hc cubed times 2 times 1.16. So now, to actually get a number, I need to know what the temperature is. So to do that, let's say, move this up here. Let's keep this here. So let's say that I use KT equals to 0.026 electron volts. So we know we get that when we have the temperature about 300 K, close to room temperature. We get KT is 0.026 eV. So let's use that. Let's also use the fact that HC is 1240 eV times nanometer. Okay. So if we stick that in, we get N over V is equal to 8 pi 0.026 electron volts. We cube that. We have 2 times 1.6, so we get 2.32 over 1240 electron volts times nanometer. Then we cube that. So if we stick that in, what we're going to get is .538, and I converted the nanometers to meters actually, so I get times 10 to the 9 inverse meters cubed. So I get 538 times 10 to the 6 photons for every cubic meter. So there's an example. So next time what we'll do is we'll look at the contribution from Einstein, how he changed the distribution that we just used for photons to include particles with mass but still have spin 0, 1, or 2 integer spin. So we'll do that next time.